viewers, welcome to Safi Mixed. In this video, I will talk about conditional probability of two correlated events. We know from our previous video on probability theory that for mutually exclusive and for mutually not exclusive events, the probability of occurrence for one event depends on the probability of occurrence on another event. In other words, the information of the probability of occurrence of one event affects the probability of occurrence of another correlated event. This behavior of probabilities of giant events leads to the definition of conditional probability. And if you don't know about this behavior of probabilities, I would suggest you to watch my first 3 videos on probability theory and the playlist probability theory. Now let's come to the point of this video. Suppose A and B are events in a sample space omega, and suppose that the probability of B, that is P of B, is greater than 0. Then the conditional probability of event A given the probability of event B is written as P A with a vertical line B and is read as PA given B equals the probability of A intersection B divided by P of B. To understand the concept of this equation deeply, let us consider the sample space of a fair dice which consists of the set of first 6 numbers. Omega equals the set of 1, 2, 3, 4, 5 and 6. Now for the dice being fair, every outcome of this space is equally probable. Let event A and B represent the subspaces given by A subspace of omega consists of the set 1 and 3, and B a subspace of omega consists of the set 1, 3, 4 and 6. Then the total probability of event A is given by P of A equals P of 1 plus P of 3 equals 1 by 6 plus 1 by 6. Since every event is equally probable, therefore for every event the net probability is 1 by 6, and if I add them together it gives me 1 by 3. And the total probability for event B equals P of B equals probability of 1 plus probability of 3 plus probability of 4 plus probability of 6, which is equal to 1 by 6 plus 1 by 6 plus 1 by 6 plus 1 by 6. Adding all of them together would give me 2 by 3. We see that these two events are mutually not exclusive as they share common elements. The information about event B does change the probability of event A and vice versa. For example, if we come to know that event B does not occur, this obviously shows that event A cannot occur either, and hence the probability of A becomes 0. On the other hand, if we come to know that B occurs, then there are 4 possibilities left, which change the probability of individual outcome from 1 by 6 to 1 by 4, thereby making the total probability of B equal to 1, that is P of B equal to 1. Now with this change for the probability of individual outcome, the new probability of event A accordingly updates to P of A equals P of 1 plus P of 4, which is equal to 1 by 4 plus 1 by 4 and is equal to half. Since A intersection B equals A, which makes probability of A intersection B equals the probability of event A, that is P of A. Now let us substitute these values in the equation for conditional probability and see what do we get. That is probability of A given the probability of B, which is equal to P of A divided by P of B, and if I replace the numerical values, then P of A equal to half and P of B equal to 1. This makes the total probability of A equal to half. This is the same result as given in equation 4. A similar procedure can be followed for mutually exclusive events.